In our last lecture, we examined the use of a dynamic vibration absorber to reduce vibration on a rotating machine. We discussed how machines that rotate often have imbalance, and this imbalance force causes the machine to vibrate at the operating speed of the machine. By the addition of a dynamic vibration absorber, we can make the machine vibrate a great deal less. A dynamic vibration absorber is essentially an elastic element, a spring, and a mass. We developed a 1 degree of freedom model of our machine, and we appended to this the dynamic vibration absorber, which was the elastic element K sub A and the mass M sub A. We found the addition of the absorber elements caused zeros in the transfer function between the force input and the displacement of the mass capital M. These zeros were on the imaginary axis at plus and minus j omega naught, where omega naught was the operating speed of the machine. This frequency was set by the stiffness K sub A and the mass M sub A of the absorber. Omega naught was equal to square root of K sub A over M sub A. We saw from the mathematics that the addition of the dynamic vibration absorber changed the transfer function in a good way. It put the zeros on the imaginary axis, and this caused the signal F, which was at that frequency, to have no impact upon the vibration of M. We've seen the mathematics, but why does this actually work physically? Physically, what is happening is that the absorber spring is exerting a force that is precisely equal and opposite to the imbalance force. The absorber spring force is canceling the imbalance force, and therefore the mass capital M is not moving. One way of looking at this is as a feedback loop, and this is apparent if we look at equations number 1 and number 2 in block diagram form. So here is a block diagram of equations 1 and 2. On the far left, you see the external force, capital F, coming into our system model. And added to it is the force from the absorber spring. This force from the absorber spring is K sub A times X sub A. The two forces are added together, and that becomes the sum of the forces acting on mass capital M. These forces then go into the transfer function 1 over capital M S squared plus CS plus K sub A. And then the output of that block is the motion of mass capital M, which we refer to as X sub S. X sub S then is input to the block K sub A over M sub A S squared plus K sub A. And this is the transfer function of the absorber between the motion of mass M and the absorber's motion, X sub A. X sub A is then multiplied by K sub A and fed back as a force to act on mass capital M, as we discussed earlier. So we've seen how the interaction between the absorber and mass capital M can be represented by a feedback loop. Now let's recall the rule that we had for feedback loops. If we have a positive feedback loop between transfer functions g and h, as shown here, then if we collapse the feedback loop and find the equivalent transfer function between the input f and the output x, we'll find that that closed loop transfer function is g over 1 minus gh. Let's now use this rule with transfer function g described as numerator p over denominator q, and transfer function h described as numerator n over denominator d. Then the transfer function g over 1 minus gh can be simplified with a little algebra to p times d divided by q times d minus p times n. So you'll note that the numerator polynomial of the closed loop transfer function will be p times d, where p is the numerator of transfer function g and d is the denominator of transfer function h. So we notice that the denominator polynomial of the transfer function in the feedback loop shows up as a factor in the numerator of the closed loop transfer function. As a consequence, the poles of the transfer function h will be zeros of the closed loop transfer function. This is why the natural frequencies of the absorber are the zeros of the transfer function between the applied force to mass capital M and the motion of mass capital M. If this is not clear to you, I'd like you to go back and restudy what we just covered. I want you to study how the block diagram that we saw arises from the equation of motion. And I want you to understand how the poles of the system in the feedback loop, what we refer to as H, how those become the zeros of the closed loop transfer function. Let's now take a look at a dynamic vibration absorber demonstration. In this system, we have a rotating imbalance on top of a platform. Hanging down below is the absorber. The rotating imbalance will shake the platform in a horizontal direction. The absorber will act to reduce this shaking, and if the frequency of rotation of the imbalance is the same as the natural frequency of the absorber, the platform will not vibrate. So here's a cartoon of our physical system and the mechanical systems model. In the cartoon, we have the rotating imbalance on top, and you can see there's the force from the rotating imbalance, and I've drawn it acting in the horizontal direction because that's the direction in which we see the imbalance causing the platform to move. The motion of the platform here is called x. Hanging down below is the absorber, and its motion is labeled xa. The model of this system is as shown here. We have the input force from the imbalance, labeled F, acting upon the mass of the platform and rotating machine, labeled cap M. Cap M is connected to the ground through the stiffness K, and this stiffness represents the supports of the platform. The dynamic vibration absorber consists of mass MA and spring stiffness Ka. We will look at the frequency response of two transfer functions. Both have input that is the force coming from the rotating imbalance, labeled F. The outputs that we're interested in are the motion of mass cap M and the motion of the absorber mass M sub A. The poles of this transfer function between F and X, or between F and XA, are the same, and these poles will be lightly damped. We'll represent them on the imaginary axis, but in reality they will be slightly in the left half plane because of damping that's naturally present in the system. These poles are represented in the complex plane diagram shown in the lower right, and they're labeled 1, and 3. Of course, these come as complex conjugates, so we get poles on both the positive and negative imaginary axis. These poles are represented in the frequency response by the peaks in the magnitude, and you see peaks at the same frequencies in both transfer functions. The transfer function between f and x in light blue, and the transfer function between f and xa in darker blue. Now you'll notice one important difference in these two transfer functions, and that is the sudden drop in gain at frequency omega naught in the transfer function between f and x. This is due to the zeros of that transfer function, which we talked about before, are the square root of k sub a over m sub a. So you'll note the following important fact about the dynamic vibration absorber. It only reduces the vibration over a very small interval of frequencies. And this is why it's important to use a dynamic vibration absorber on a system that will tend to be rotating at only one speed. Perhaps it's 3600 RPM, which corresponds to a 60 Hz excitation in the motor coils. The dynamic vibration absorber cannot reduce the vibration response across a wide range of frequencies. It's strictly a narrow band device. Let's now look at the results from the experiment.
Here we've got another single degree of freedom spring mass system where the forcing function, in this case we've got an imbalanced mass which is being spun. Although we're spinning it with fairly significant vibrations, it's not moving much because we've got a tuned spring mass dampener right here. So his resonant frequency is exactly the speed that we're spinning at right now. So Bob, the maintenance man here, can stand on the top of the building with the imbalanced air conditioning unit and not experience too much vibrations. If we spin it at a different speed, I'll adjust the speed now. Now you can see there's much more significant vibration at the top of this because we're no longer operating at the resonant frequency of the tuned mass dampener. And here you can see we're very far away from the tuned frequency and we're getting significant vibrations of the building due to the imbalanced mass. Because at this frequency we're significantly lower than the resonance frequency of the spring mass system, it's essentially moving in phase with the larger mass, which is the imbalanced mass moving at the force function. In this case, it's not doing anything to dampen the vibrations because we're so far below its resonance frequency. It's simply moving in phase with the imbalanced mass. As we increase the frequency towards the frequency of the tuned mass dampener system, it will continue to oscillate. Its amplitude will increase, but the amplitude of the table will decrease. You see here we're getting very near the frequency of the tuned mass dampener, and the frequency at the top, the motion, has almost completely ceased. Here's a top view. This is the servo motor, and here's the imbalanced mass, which is spinning. Right now it's spinning at the resonant frequency of the tuned mass spring system down here, which is vibrating. The vibrations are being basically all absorbed by the spring mass system at the bottom, so that this upper plate is almost stable.